see Tiago Campante, which is a talk that has been shifted from tomorrow to now.
Okay, so good afternoon, everyone. Today I will be talking about a truly fascinating system of 5 sub-Earth-sized planets whose origin dates back to the dawn of the galaxy. In the next 15 minutes or so, I will try to combine knowledge from astroseismology, exoplanetology, and even some galactic astrophysics to offer you a detailed picture of this system and to present the broader implications of such a discovery. So KOI-3158, the parent star in this system, is a high proper motion K-dwarf. It is also the closest and the brightest multiple planet system detected so far by Kepler. We acquired a high resolution spectrum with a higher spectrograph, showing that it has only 30% of the sun's iron content, while being overabundant in alpha process elements for a star of its metallicity. KOI-3158 is a member of the Galactic thick disk. So here we show a proxy for alpha element abundance versus metallicity in the low metallicity regime. So KOI-3158 is denoted by a blue star. Blue triangles represent Kepler planet candidate hosts, and black dots correspond to stars without planetary companions, observed in the context of the HARPS GTO Planet Search program. Okay, this dashed line follows the well-established galactic trend of increasing alpha enhancement with decreasing metallicity. And it also marks the fiducial chemical separation between thick disk stars above the line and thin disk stars below. So it is well known that thick disk stars are overabundant in alpha elements relative to thin disk stars in this low metallicity regime. So KOI-3158, being a member of the thick disk, lies above this dividing line. In this next plot, we show a so-called tumor diagram, so displaying all exoplanet hosts in the Extrasolar Planets Encyclopedia, for which it was possible to derive galactic space velocities relative to the local standard of rest. So KOI-3158 is, to the best of our knowledge, the exoplanet host with the second largest peculiar velocity, only after Campante star, which is a member of the galactic halo. Note that Campante star falls out of the plotted range here. KOI-3158 is also a member of the Arcturus stellar stream, which is a moving group of stars from the thick disk. So the origin of the Arcturus stream has been the matter of debates. So it was originally thought to be of extragalactic origin as a result of a merger event. However, its members are chemically similar to thick disk field stars, which in turn have abundance properties different from those of satellite galaxies in the local group. So consequently, the Arcturus stream started being interpreted as arising from dynamical perturbations within the galaxy. Okay, so a fainter companion was detected on the Iris guide camera at an angular separation of about 1.8 arcseconds. So it means it is unresolved in Kepler observations. And so we conducted follow-up observations using the RoboAO system to determine the amount of dilution of the light curve due to the presence of this companion. Okay, the two components in the system are co-moving, as implied by their systemic radial velocity. And after cross-correlating the spectrum of the secondary, we found out that it in fact comprises 2 M-dwarfs. So that means that KOI-3158 is the primary star in a hierarchical triple system. We also detected solar-like oscillations in the flux time series of KOI-3158. Interestingly enough, it is the star with the highest large frequency separation ever measured, to the best of my knowledge at least. We then went on to determine stellar properties by matching global asteroseismic parameters and spectroscopic observables to grids of stellar evolutionary models, and we show the results here. And I would highlight the small relative uncertainty on the stellar radius, which is of course crucial to obtaining precise planetary parameters from transit observations. But not only on the stellar radius, but also on the stellar mean density, which will later be used as a strong prior in the transit fit. Detailed modeling of frequencies of individual modes of oscillation, or their combinations for that matter, can lead to considerable more precise estimates of the stellar properties, and most notably the stellar age. Okay, as a preliminary step, we extracted frequencies from the power spectrum using an MCMC fitting procedure, and very interestingly, we came to the conclusion that we needed to correct these observed frequencies for the Doppler shift due to the line of sight motion of the star. And I'm probably right if I say that most of you astroseismologists have never considered this correction, but given the increased precision, frequency precision in the CoRoT Kepler era, this correction can be indeed significant. And that's the case for this particular high proper motion star of the order of 10 sigma, mind you. Okay, so to sum up, the star, and hence the planetary system, has an age of 11.2 billion years with a relative uncertainty of 8%, so plus minus 0.9 billion years. Of course, the results come directly from detailed frequency modeling, which makes KOI-3158 the oldest known system of terrestrial-sized planets. We investigated the planetary properties of this system using 4 years of long cadence data that virtually span the entire duration of the Kepler nominal mission. And we did that by fitting a 5-planet transit model to the Kepler data using an affine invariant MCMC algorithm. And you can see here the best fitting model as a red curve plotted over the phase-folded transit data for the 5 planets in the system. In this figure, we compare the size of the planets in this system to those of the solar system's inner planets and members of the Kepler-37 system. And recall that Kepler-37b is the smallest known exoplanets. So KOI-3158.01 is the innermost and the smallest planet in this system, within 2 sigma of the size of Mercury, and its radius has been measured with a precision of 100 kilometers. That's just amazing, mind-blowing. The intermediate planets are the size of Mars, and finally, the outermost planets has a size intermediate to those of Mars and Venus. So KOI-3158 expands the population of planets being found in low metallicity environments from the mini-Neptunes that were recently found around Campante star to the domain of terrestrial-sized planets. This system is also highly compact, both in terms of its architecture and in a dynamical sense. So all planets orbit the parent star in less than 10 days, or within 0.08 astronomical units. That's roughly 1/5 the size of Mercury's orbit. And furthermore, all adjacent planet pairs are very close to being in exact first-order mean motion resonances. So here we show several highly compact multiple planet systems. They are characterized by a concentration of dynamically packed planets near 0.1 astronomical units. And notice that all the planets in the KOI-3158 system are interior to the orbit of the innermost planet in the Kepler 11 system, which is the prototype of this class of highly compact systems. Compact systems, they make up approximately 1% of all Kepler planet candidate hosts. Okay, so the proximity of each planet to a strong resonance indicates that the system evolved dynamically after the formation of the planets. And a likely mechanism to explain such a configuration would be convergent inward migration. The damping of the orbital eccentricities would, due to tidal evolution, would then tend to push the orbits wide of exact commensurability as observed. This is, of course, a very simplistic view that needs further scrutiny, and I'm sure that this will become a very interesting case study for those of you working on planet formation and migration. Okay, there are several lines of evidence that validate this system as being a true 5-planet system around the target star. So first of all, we invoke statistical arguments based on the system's high multiplicity to rule out chance alignment blends such as background eclipse environments. Also, given the target star's high proper motion, a sanity check would be to look at archival images of the region where KOI-3158 currently is, and we don't see any background stars in that region down to the confusion limits of the images. Second, and most importantly, I would say, the non-randomness of the observed multi-resonant chain asserts that all 5 planets form a single system around the same star. And finally, we established that the planets transit the target star, not one of its M-dwarf companions, and we did that by testing the dynamical stability of the 5 planets if they were to all orbit either of the M-dwarfs. And we came to the conclusion that such a hypothetical system would become unstable within very short time scales. Okay, so I will conclude with a couple of slides that convey the broader implications of such a discovery. So the chemical composition of stars hosting small planets, and by small I mean planets with radii less than 4 Earth radii, seems to be more diverse than that of gas giant hosts, which tend to be metal-rich. So that implies that Earth-sized planets may have readily formed at earlier epochs in the universe's history when metals were more scarce. KOI-3158, a system of terrestrial-sized planets, formed when the universe was less than 20% of its current age. So that suggests that Earth-sized planets may have formed throughout most of the universe's history, leaving open the possibility for the existence of ancient life in the galaxy. Also, there is growing evidence that the critical elements for planet formation in low metallicity environments, or iron-poor environments, if you will, are alpha process elements. So as we have seen before, thick disk stars are overabundant in alpha elements relative to thin disk stars in the low metallicity regime, which may explain the greater planet incidence among thick disk targets for metallicities below half that of the Sun. So, thick disk stars were thus likely hosts, or among the hosts, because I'm not forgetting about high alpha halo members. So among the hosts to the first galactic planets. So the discovery of an ancient system around the thick disk star KOI-3158 confirms that the first planets formed very early in the history of the galaxy, and may help us pinpoint the beginning of what we may call the era of planet formation. Okay, so at last, I would like to thank all my fellow co-authors. Many of them are here today in this room, without whom this work would not have been possible. Thank you very much.
Thank you, Tiago. Questions here.
I was surprised by the precision that you put on the stellar modelling. Could you tell me whether that is agreement between different modellers or the average of different values by modellers?
It is due to a perfect agreement between different modelers.
Yes. Sorry?
So, Garstech provided the central value for the H, and the dispersion around that value of 8% means that the agreement among the several codes or pipelines that contributed was exceptional.
So what constraints did you put on it?
I'm sorry?
What constraints?
There are several ingredients going to the models, but one prerequisite was the inclusion of atomic diffusion. And of course...
Sorry, can you? Inclusion of?
Atomic diffusion.
Ah.
Okay. That was the main prerequisite.
Okay, thank you.
When are you going to have the press release for this?
Hopefully soon.
But any further questions?
Why is there no Kepler number for this source?
Only after being accepted by a peer-reviewed journal. Yeah. But I can once more give you the kick number and the hit number if you're interested. I don't know it by heart. I'm sorry.
After acceptance.
It doesn't yet. A Kepler.
Okay.
Yeah.
Well, a further. Yeah, it will get certainly one earlier or later.
No. I was just telling that a proper Kepler number will only be assigned after acceptance by a peer-reviewed journal. Those are the rules. Those are the rules.
Before the
so for
final
now, I
submission.
have to call it KOI-3158.
Juan Antonio?
Yes, maybe you have commented on that, but is there any of these planets within the habitable zone of
Not
the,
in this system. Not in this system. Of course, it's too compact and the planets lie too close to the star for them to be habitable. Also, I should also say, because I was careful enough not to mention the word rocky during my presentation, because photometry alone does not yield planet masses. But of course, if you believe empirical mass radius scaling relations or theoretical models for planet formation, planets with radii less than 0.8 Earth radii are very, very likely rocky. Not this case, because the system lies too close to the parent star. But there may be others as old, and we don't know.
What was, maybe I didn't listen well, was there anything on TTVs being checked?
TTVs marginally for the outermost pair. RVs, even if you would combine all 5 planets in the system, the semi-amplitude would be not over 0.5 meters per second. So if you want, in terms for comparison, if you want to compare, Kepler 10b has a semi-amplitude, RV semi-amplitude of 3 meters per second. So
You
forget
must
it.
have been TTVs. I said TTVs.
TTVs, as I said, marginally detected for the outermost.
Okay. Any other question?
Did you try to look for a companion, like common proper motion in infrared, if you would find a brown dwarf or very low mass star around it in copper mode?
I mean, this is done. I mean, RoboEO works at the redder wavelengths in the visible band and in the infrared. So, of course, there is a companion. We know from spectroscopy that is co-moving. RoboEO does not allow you to disentangle the 2 M-dwarfs that actually compose the binary. Yeah. I think, we will have, actually in August, we will have a KAC-AO image for this system. And if the 2 M-dwarfs are actually separated by more than 1 astronomical unit, we will be able to disentangle, right?
So there already is a KAC-AO image that I took.
No, there will be.
No.
We'll get it in 1 month.
No, there is, because it's
well, a new one.
no, because it's already on CFOP.
Yeah, in CFOP we have several stuff there. Yeah.
So anyway, so it's just 2 stars at the resolution of KEK.
It is.
And you're well, I don't know. Did I take that for you, Tom, or did I take it for me? Whatever. You're more than welcome to use it. It's on CFOP, so you can use the KEK image.
Yeah.
Be my guest.
Yes.
Sorry to interrupt your answer before.
Okay, and I think one last question.
So the companion is very close, right? It's only like
The
within 100
companion,
AU.
the orbit should be around 400 years.
Okay, so it's within 100 AU.
Of course,
Companion, yeah.
assuming circular orbits.
Sure. Do you have a constraint on the mutual inclination of the 5 planets?
Yes, we have the inclination of the 5 planets, and if we translate that into a minimum mutual inclination, that would give us 2-3 degrees. But of course, you would expect that, because this is a multiple system, they have to be nearly aligned.
Okay, thank you.
Okay. Yeah, thank you again.